You're welcome.
Mm. Good afternoon, guys. Sorry about yesterday. I was waiting for some 2 people at least we get started.
I'm waiting for our colleagues and then Alice will start.
But basically, we had started on what we call latent heat.
And give them 3 minutes today and then we'll start this.
So you're welcome once again. We had introduced latent heat, and we talked about some of the key definitions. Among them was latent heat itself, which is the amount of heat you require to change the state of a substance without a change in temperature. Then we also had specific latent heat or latent heat of fusion, which is the amount of heat energy you require to change the state of a substance from a liquid to solid or solid to liquid. Then it became specific when we looked at 1 kilogram mass of a substance being converted from solid to liquid or liquid to gas. Paul. Huh? So with that regard, sorry, I had to shift a little. So we talked about melting, and we said melting is the process by which a solid changes into a liquid at a constant temperature. We also have what we call freezing. I think I forgot to mention this. Freezing is the process of converting a liquid into a solid at a constant temperature. Both of these two occur at a constant temperature. The temperature of solidifying is the temperature of liquidifying. So if you want to solidify it, you take it at temperature. If you want to liquidify it, you take it at temperature. That's why we are saying they occur at a constant temperature. I gave you the explanation for melting, how it comes about. whereby I said molecules of a solid are closely packed together, and the intermolecular forces of attraction between them are there coexisting as a result of cohesive forces, and those are very high forces, whereby the molecules vibrate about mean positions or fixed positions due to the thermal agitations of the molecules and the atoms of the solids. When the temperature is increased, for example, in a solid, the molecules gain more kinetic energy. This kinetic energy makes them over-vibrate about fixed positions. And as they over-vibrate, they break the bonds between them, and the intermolecular forces of attraction are reduced. So with this, the attraction forces are overcome, and then the bonds are broken, molecules start weakening in terms of their bond together. So when they weaken, they start giving themselves space. And at the end of the day, the solid therefore converts into a liquid. And remember, liquids have slightly spaced molecules that are freely randomly moving, not so far like those ones of gases, while for those ones of solids, they're always packed together. So that compactation is one which has been destroyed by increase in temperature. Now, during melting, the temperature remains one constant. What happens during melting? Temperature remains constant. I've mentioned that. Because all the heat supplied is used to overcoming the intermolecular forces of attraction. Because all the heat is used to overcome the intermolecular forces of attraction. And hence weakening the bonds. Then at the melting point, when you have what to call a melting point, back sweater again. At the melting point, both the solid and the liquid coexist in thermodynamic equilibrium. When we say thermodynamic equilibrium, it means that they are existing at the same temperature gradient. They are existing at the same temperature zone. That's why we say they are in thermodynamic equilibrium. So for any system to be in thermodynamic equilibrium, the amount of heat energy gained is supposed to be equal to the amount of heat energy lost. Or the temperature should be averagely the same. For example, when you look at there's this illustration we normally talk about the sun. A sun, we know a sun looks like something like this. But as this sun shines, it has some very dark cold points which were noticed on it. Those very dark cold points, they counterbalance the heat which is produced by this burning of the sun, and at the end of the day, they make the whole system of the sun to be in thermodynamic equilibrium. So that's what I'm calling thermodynamic equilibrium. A situation of making sure that the system does not lose the heat up to or beyond, below or above a certain temperature. So the system has to maintain a certain temperature, and that state we say it is in the thermodynamic what? Equilibrium. So here both solid and liquid exist in thermodynamic equilibrium. So having identified those about melting, can go ahead and talk about determination of latent heat of fusion of ice using the method of mixtures. I will send you the notes. Determination, latent heat, specific using method of mixtures. Still, we can use a vessel which is well lagged. This is the thermometer. The stirrer, the thermometer. This is the calorimeter. This is our lagging. Remember, the lagging prevents or protects it from losing heat. This could be our water. Now, a calorimeter of known specific heat capacity, CC. This is the specific capacity of the calorimeter. Is weighed when empty. You first weigh it before putting in the water, and you get its mass, become MC, which is mass of the calorimeter. It is half filled with warm water of known specific capacity, specific capacity of the water. And then it is reweighed. Now when it is filled with halfway the water. Remember at first we measured it, we weighed it without water, now we are weighing it with water. So the mass of the water can be attained. The water is stirred until, when you stir the water, you shall have what? The initial temperature, θ1. But this initial temperature of the water, remember this water comes and touches the edges of the calorimeter, okay? So the temperature at which this water is the same temperature at which the calorimeter is. So at the end of the day, you shall have the same temperature for water and the calorimeter initially. Then after which, drop small ice tubes. Let me assume this is my ice. Small ice cubes are dropped in now. You're getting all those initial drop measurements. So you drop in the ice, these are our ice cubes. What happens? We are dropping in small dry chips of ice, but which kind of ice? The ice we are talking about is what we call dry ice. The reason why we use dry ice, I told you dry ice, if you want to test dry ice, go to your fridge at your home, in a freezer, put there an ice rack. Let it be there like up to morning, then pick it and put it on your tongue. It gets stuck on the tongue, then it is dry ice. It means there is no slippery. If it was slippery, it would slip off. But the dry ice can get sticky. Yeah? So that's how dry ice looks like. So you put in droplets, small droplets of crisps, of chips, of dry ice, so that all the melting, all the water that is going to come out, all the melting that will take place will basically come from the ice only we had before. So all the heat will be gained by the ice from the water. When that dry ice is at 0 degrees Celsius, and then are added one at a time to the water. So you drop in one by one. Don't just get a bunch and then pour all of it. Just drop in one by one. Water is stirred again, so you stir again, yeah, until each ice piece melts. So whenever you drop one, you stir. Drop another, you stir. Drop another, you stir. After some time, a final temperature θ2 will be attained. Final temperature θ2 will be attained. Now, here what is going to happen is the calorimeter and the water, remember they were at a temperature θ1. They are going to lose the heat. So the equation statement will be heat lost by water and the calorimeter is equal to heat gained by ice, or is equal to heat. Now, how does the ice gain heat? Heat gained by ice is equal to, first of all, I'd forgotten, heat energy for latent heat is mass times latent heat of fusion, where latent heat of fusion of ice is 336,000. Okay? Sometimes it is 3330. So, to gain the ice, first of all, melts. Ice melts using latent heat of fusion, which is MLF. Plus, the temperature of ice now is going to rise up to temperature θ2, the final steady temperature. So it will be mass of the ice, the specific capacity of the water, times temperature change. Actually, this is supposed to be 0, because when the ice came in at 0, when it gets a new temperature θ2, becomes MI LF plus MI CW into θ2. Why does the 0 go off? Because 0, of course, when you subtract it off, you get the same item. So from here, you can make latent heat of fusion the subject, which shall be heat gain, heat lost by the water and the calorimeter is equal to mass of the water, specific capacity of the water, temperature change from θ1 minus θ2, plus mass of the calorimeter, specific capacity of the calorimeter, temperature change θ1 minus θ2. One may wonder, why am I saying θ1 minus θ2? The original temperature of the water was higher. When ice was brought in, the water becomes colder, so the temperature drops. So the higher temperature minus the lower temperature gives you the change in temperature. And in that regard, the higher temperature is θ1. It's supposed to give us mass of ice times latent heat of fusion of ice plus mass of ice and the specific capacity of melted ice. Melted ice becomes water times θ2. So make LF the subject. To make latent heat of fusion the subject, we get mass of water, specific capacity of water, plus mass of the calorimeter, specific capacity of the calorimeter, times θ1 minus θ2 minus MI, mass of the melted ice. This is melted ice. Specific capacity of the water times θ2 divided by mass of the melted ice. All this was mass of melted ice. Okay. So with that, you can get a value of latent heat of fusion with using the method which we call the method of mixtures. It's all about, one, getting a liquid in a calorimeter, stir that liquid to have a uniform distribution of heat. Of course, the liquid, you should know its specific capacity. You should know the specific capacity of the calorimeter. You should know the mass of the calorimeter when it's empty. Then you should also know the mass of the water. Okay? So, the second one is, second method is determination of latent heat of fusion using the electrical method. So using the electrical method, one, I told you the electrical method has one challenge, the diagram. When you draw it wrongly, my voice might not be so clear. COVID is on my case. So the rheostat, which adjusts the voltage and the current. The switch K. The switch is not closed, the entire system is wrong. The experiment cannot take place. This one is what we call the dry ice. This is a heater. This is melted ice water. So, in this method, you get dry ice at 0 degrees Celsius, and you place it in a funnel, and then you place there a heater. And then you have to switch K on, close it. You have to close switch K, simultaneously start the stop clock. Once you close the switch, start the clock. Then melted ice is collected in a beaker of known mass. This is a beaker. This beaker you are collecting in here melted ice, which is water, okay? That is passing through a funnel. When sufficient ice has been melted for some time, stop the clock. And the time which it has taken place is recorded. That time can be T. The ammeter and the voltmeter readings are read at that instant. So you read the voltage here, read also the current here. Respectively. The mass of the ice melted is is measured and recorded. So what you do, you go and measure the empty beaker, get its mass, come and measure the mass of the water melted from ice plus the beaker together, then after you subtract, that's how you get the mass of the liquid. So in this case, heat is supplied by the electrical heater. So heat supplied by the electrical heater is equal to therefore, heat supply by the electrical heater is equal to heat gained by ice. So heat energy is I, V is power times time, is equal to mLF. So latent heat of fusion will be over M. So there you can define the specific latent heat of fusion. Now remember I mentioned earlier that freezing is the process in which a liquid changes into a solid at a constant temperature. During freezing, latent heat is given off and compensates for the intermolecular forces of attraction. Now, what does that mean? When an item is converting from liquid to gas, yeah, we do a lot of work in bringing these molecules together. So when you do bring the molecules together, you are going to build bonds between the molecules. When you build these strong bonds between the molecules will hold themselves in certain positions that will not easily distort their shape. So at the end of the day, the system or the item now moves from a liquid to a solid. From there, we can go to what we call latent heat. Of vaporization. Latent heat of vaporization should be Z. Now for vaporization, it's the quantity of heat energy you require to convert a liquid to gas or to convert a gas back to a liquid at a constant what? Temperature. Now you know in heat there are so many explanations. So there is this explanation for you to explain how evaporation takes place. Now to start with, liquids have molecules which are closely relatively to each other. They are not so spaced away from each other and they are not so compacted. So they are relatively close to each other. There exists weaker intermolecular forces between them of attraction. The molecules are randomly moving also, though not so random as those of gases, but they are free to move. They have some weak intermolecular forces of attraction. Now, when the temperature of the liquid rises, what happens is these molecules gain kinetic what? Energy. When these molecules gain kinetic energy, their energy is going to increase. So what happens is the molecules gain more kinetic energy and move about the liquid body with high velocity. So they start moving faster. When they start moving faster, the surface molecules with the maximum kinetic energy overcome the attractive forces, and when they have overcoming the attractive forces at the surface, they are in position to escape in form of vapor. So, what does that mean? It means that even if it's cooking water at home, the normal boiling, we shall also explain boiling. When you heat up a liquid, water for example, you see bubbles rising from the bottom of the surface. Those bubbles behave like molecules. So the most energetic ones which gain energy, they rise to the surface. When they rise to the surface, as they are moving through the bulk of the liquid, they are still getting attraction from other liquid molecules. But when they reach the surface, they break that molecular bond of attraction between the other molecules, and they convert themselves to another form, and by that they escape from the surface. So it implies that only those that are energetic enough are the ones that are free to escape in form of vapor. Otherwise, vaporization cannot take place if molecules are having less what? Now, evaporation also occurs at a constant temperature. Why? It's because the heat is used to heat supply is used to break the bonds between the liquid molecules and overcome the forces of attraction between them and the external atmospheric pressure. So they can ask you to explain. But before I ask you to explain, can we define these definitions? Latent heat of vaporization, specific latent heat of vaporization. Specific latent heat of vaporization is the amount of heat energy required to change the state of 1 kilogram mass of a substance from a liquid to gas. I can ask you to explain why latent heat of vaporization is greater than latent heat of fusion. Latent heat of vaporization of water is 2.26 and 10 power 6. Latent heat of fusion is 3. So you see that this one is bigger than this one. So I can ask you why. Why is latent heat of vaporization greater than latent heat of fusion? Okay. Basically, these are the reasons. One, latent heat of vaporization is used to overcome the intermolecular forces of attraction. Yeah. And also, it is used to make the water molecules break free from the bonds between the liquid molecules. Whereas latent heat of fusion is used to overcome only the intermolecular forces of attraction and to weaken the bonds between the molecules. While for the other one, what happens is we do work in one, breaking the intermolecular forces of attraction, and also break the bonds which the molecules are combined. In that case, some of them will end up escaping. We have an experiment to determine latent heat of vaporization. I can ask you to describe an experiment to determine latent heat of vaporization. I'll send you a better write-up in the notes. This is where our source of steam is. This one uses steam because of vaporization. Then the steam will rise. This is a vapor. This is the flask. This is the water. So steam passes through this exit. Then it comes and goes into what we call a steam trap. So the steam comes through and meets this steam trap, which will trap it down to the liquid. The stirrer. This vessel is lagged to assume that no heat is lost to the surrounding. And this one is a thermometer. So the calorimeter of non-specific heat capacity, CC, is measured when empty. So you get the mass of the calorimeter when it's empty. And is recorded. Then it is also half filled. This is our calorimeter. It is half filled. With cold water of mass MW. The water is stirred and its initial temperature θ1 is recorded. So when you stir the water, the initial temperature can be determined. The water in the flask is then heated up. So we start heating this water and it evaporates. The vapor formed is let into the calorimeter. So you bring the vapor to come and enter here. So when the vapor enters into this vapor trap, what is going to happen is it's going to be let into the calorimeter. So it's going to come down here to come out like this. So when it comes out like that, the mixture in the calorimeter is then stirred. So you stir it using this stirrer. Then you get the final temperature θ2. The calorimeter and its contents are then weighed again. That determines the mass of the condensed what? Vapor. Now remember earlier on we measured mass of the calorimeter. We put there water and we measured. Now we are putting there steam. So we need to find out the change in mass. That change in mass comes as a result of the mass of the steam. So to get mass of the steam would be IM. mass of steam. Therefore, heat lost by water vapor is equal to heat gain by the water plus the calorimeter. That is our equation statement. So heat lost by water vapor will be, the vapor first of all loses heat by latent heat of vaporization, which is MLV. Then plus mass, let me call it MV, mass of the water vapor. The vapor after liquidifying, for example, it will be a liquid at 100 now. When it's a liquid at 100, the temperature is going to drop to a new temperature, theta 2. So it becomes water, specific capacity of water. Temperature change will be theta, will be 100 minus theta 2. Is equal to heat gain by the water, capacity of the water. Temperature change of the water will be theta 2 minus theta 1, because for them temperature is increasing. Mass of the calorimeter, specific capacity of the calorimeter, same temperature. We are looking for latent heat of vaporization. It will be mass of the water, specific capacity of the water plus mass of the calorimeter. This was calorimeter. And theta 2 minus theta 1 minus mass of the vapor, specific capacity of the water from condensed vapor, and temperature change. Then now all of this can be divided by the mass of the vapor. Out of mass of the vapor. So with that, you can get latent heat of vaporization using the method of mixtures. That is a mixture of vapor and water. Let's take a look at an example. We can call it a day. I'm going to tell you the write-ups of these experiments. A steam 100 degrees Celsius is passed into a copper calorimeter mass containing 340 grams of water at 150 degrees Celsius. This is done until the temperature and its contents is done until the temperature of the calorimeter. Let me remove this one. and its contents. It says the steam at 100 degrees Celsius is passed into a copper calorimeter of mass 150 grams containing 340 grams of water at 150 degrees Celsius. This is done until the temperature of the calorimeter and its contents is 71 degrees Celsius. So there is a drop in temperature. If the mass of the calorimeter is found to be 525 grams, calculate the specific latent of vaporization. Hope you know that is specific latent specific capacity of copper of the calorimeter. So can first have that equation down. The specific capacity of copper has been given as 400. We have temperature at theta 1, which is 100. 100 is dropped to theta 3, which is 71. We have theta 2, which was the initial temperature of the water, and the calorimeter, which was 150 degrees Celsius. No. It was supposed to be 50, not 150. So heat loss by steam is equal to heat gain by water So the equation statement says heat lost by the steam, because the steam is going to lose the heat. But as it is losing heat, what is it losing it to? It's losing the heat to the water and the container in which the water is being contained. But as steam is being lost, we have this part. As heat is being lost, one, we lose heat until so heat lost by steam shall be mass of the steam, latent heat of vaporization, plus mass of the condensed steam, specific capacity of water times the temperature change, which should be θ1 minus the final temperature θ3. When this is going to give us what? Heat gained by the water, mass of the water, mass of the water, temperature change is θ3 minus θ2, plus mass of the calorimeter, specific capacity of the calorimeter times θ3 minus θ2. So we are looking for latent heat of vaporization. Can make latent heat of vaporization the subject. We get M water, C of water, plus M calorimeter, C calorimeter, times θ3 minus θ2, divided by or minus. I have moved this one this way. That's why you get a minus over mass of the steam condensed. So latent heat of vaporization will be mass of the water is specific capacity of the water is 4200. Mass of the calorimeter is and the specific capacity of the calorimeter shall be there is a temperature difference between those two, which is 71 minus 50, plus mass of the water. But this water is condensed steam.
Excuse me, teacher.
Yes, please.
I was asking, don't we first change the grams into kilograms? The masses.
We can convert them, but the challenge is, even if you convert, even this one down, you'll convert it. So it will give you the same divisor. So over 1,000, over 1,000, over 1,000, over 1,000. You factor out over 1,000, over 1,000 down. You get the same answer.
All right.
Okay? But if it was asking like for specific heat capacity or temperature change, there you have to straight away convert. Or if it had the power here, there was heat supplied from a power source. You use IVT, there you have to use M in kilograms. But here where you have M throughout, you can assume M has been converted already. So plus, no, not plus, this is minus mass of condensed steam the mass of steam is 150. The mass of the copper calorimeter is 525, not this one. So we shall have 150 times 4200 times the temperature change from 100 to 50 to 71. 100 to 71 is 29. Now all of this is what we are dividing by mass of steam, which is 150. Can you now press the calculator and give me the answer?
Excuse me, teacher.
Yes, please.
Teacher, the mass of the calorimeter is the one which is 150. And then the mass of the
No,
calorimeter.
listen to this. They said a steam of 100 degrees at 100 degrees Celsius is passed into a calorimeter of mass. Oh. No, let me see. Hey, you're right. We don't know the mass of condensed steam, do we?
No.
I don't want to overlook this page. Let me try it again here. Yeah, I've got your point. I think I missed out something. In actual sense, it's like this. This was mass of the calorimeter, empty, 150. This was correct. They told us if the mass of the calorimeter is found to be 525, so mass of condensed steam shall be mass of the calorimeter plus condensed steam minus mass of the calorimeter, which is 525 minus 150. What do we get? What do we get?
Yeah, 375.
Huh?
375.
Correct, 375 grams, okay? Now, hey, actually, wait. Listen to me. There is a mass of the calorimeter. One of 50 plus 340, what do you get? That is 490. This is water plus the calorimeter. Now, it is what we are supposed to subtract off. Is what gives us the mass of the condensed steam, because I was seeing condensed steam being bigger than the water, and I was wondering. Are you getting my point? They said copper calorimeter of mass 150 containing water of this. After, if the mass of the calorimeter is found to be now this one consisting of this and this. But if you take away this and that, the balance should be steam. Is the argument okay now? Guys, are you getting my argument? This was in the calorimeter. This is the mass of the calorimeter. This was in the calorimeter. After some time of condensing the steam, the calorimeter was weighed to be having this mass. But this mass partially has this one and that one. So if you remove these two, the remaining mass becomes the mass of the condensed steam. Are we together? Guys, do you confirm that?
Yes.
Yes.
Can we subtract now this one? You get what? 35.
35.
Okay. Now let us substitute here. So we can substitute like the way you wished. Those of us who wanted to use kilograms. This is mass of the water was 0.34 times 4,200 plus mass of the calorimeter 0.15 times specific capacity of the calorimeter 400 times the temperature change theta 3 minus theta 1 minus theta 2 21 minus mass of condensed steam 0.35 times specific capacity of the water from condensed steam times 29. Temperature change will be 29 from 100 to 71 divided by mass of the condensed steam, which mass is 0.35. But like I said, if you had divided everything by 1000, it would reduce back to what I had written earlier. So can you get LV?
Teacher, 35 divided by 1000 is 0.035.
Hey. Yeah, you're right. Include it and then we see the answer.
It's 2.59.
2.2 times 10 power
6.
6, don't so? And remember,
Yes,
the exact one is 2.26 and 10 power 6. So sometimes if you're working out something like this, and you already know what latent heat of vaporization is, then you should know what the answer to which you should work towards. If it's latent heat of vaporization, it is 334. And remember, we asked ourselves, why is this one bigger than the other one? It's because this one does work to break the bonds and also the energetic molecules to move away. The other one only does work of breaking what? Bonds. Sorry, campaigns are everywhere. Sorry about the sound interference. So today I will stop here. Let me send the write-up of the experiments. Tomorrow we shall start with latent heat of vaporization. And I'm also going to send some more numbers. Unless if someone has a question. Okay, if no questions, I think we can stop there for today. This is my okay.